Good morning, good afternoon, good evening, everybody, wherever you are in the world. And it gives me great pleasure on behalf of my co-organizers of the EMinar series, Stefan and Max and Kate, to bring you the very first one of season 2. And we're very happy to have Mark Everett giving the first seminar. And basically, we should all know this, the theory of EM induction. Mark is going to walk us through this. And before I introduce Mark, let me just remind you that you can go on to the EMinar webpage on MTNet, and there you'll see all the EMinars that are being listed for season 2. And for each EMinar, you'll see, and for the upcoming ones, you'll see registration links if they've been set up already. And for past ones, you'll see a video link and a presentation link. So you can see all the season 1 EMinars, and then as soon as this is finished, you'll see Mark set up. Just a quick reminder, as this is the first EMinar to everybody, that we are on a Zoom webinar, and this means you have these controls. You can control your audio settings, where your sound comes out of, or you can send a chat message. You can raise a hand at the end if you want to actually physically or verbally speak to the speaker. And then the Q&A, you can send questions. Now, Mark, it will be answering questions at the end. So I would ask you not to ask questions immediately in the middle of the seminar, because you might find your issue is addressed by Mark at the end of the seminar. Okay, or during the seminar. So again, just it gives me great pleasure to introduce Mark. I've known Mark for many years, since he's a student of Nigel Edwards at UT. So here's his brief CV. Physics, a lot of us with an EM background actually came through physics, bachelor's and master's, and then worked with Nigel at Toronto, and then went off to work with Steve and Bob at Scripps, and then with Adam in Cambridge. So you can see he had a wonderful background, and then moved to Texas, where he's been since 1995, so 26 years now. But he's popped off away to various places, ETH and Thailand. That's a nice idea. And he got a Best Paper Award in 2019 with Alan Chave, describing his paper on EM induction. Since 2013, he's been co-editor of Journal of Applied Geophysics, and he is a registered professional geoscientist. So without more ado, let me just clear this and invite Mark to show yourself and share your screen, and take us away, Mark.
Okay, here I am. Can you see that? The screen is right here. Okay, can everybody see that?
Yep.
Okay, well, thank you, Alan. I'll go ahead and start for the introduction and for the invitation from you and your colleagues. It's a great privilege for me to be able to speak to this group today. And as you know, the title of my talk here is Theory of EM Induction. The acknowledgements, Alan's already mentioned most of these people. So while you're looking through the outline of some of the topics that we'll discuss today, I just want to affirm that the folks at the bottom here have been very instrumental in my career, and there's many others over the years, including Alan and others who've really helped me a lot. So my gratitude goes out to those guys. Before we get into the subject matter proper, I'd just like to offer this preliminary thought. After 26 years of teaching at a public institution, you have to explain difficult concepts every now and then. And what I've learned over the years is that these difficult concepts are often best understood when they're either learned or explained in different ways. For example, here's a concept in words. Here's another concept in equations. It says more or less the same thing. And here in pictures, we see that a golf ball is at rest until it's acted upon by a rather large impulsive force when suddenly it moves. And none of these techniques for learning or explaining things is inherently superior in all respects. In fact, it's probably a combination of these modes that can best advance your advanced knowledge of students or even of experienced researchers. So I don't need to go into great detail about what is the electromagnetic induction method. So I'm going to be fairly move through this quickly. We all know that time variations in an external magnetic field induce electric currents in the conductive earth. These external magnetic fields can be natural or they can be man-made. In the latter example, we can think about active source methods, and in the former, passive methods such as magnetotellurics, which measures the response of the Earth to natural fluctuations of electric current systems, for example, in the ionosphere shown here. And over here is an example of some kind of electric current system set up in the ionosphere, in this case by solar heating from the sun. It's the SQ daily variation. And the data that one gets at the surface can be used to probe depth ranges of tens of kilometers to thousands of kilometers, which is interesting for those interested in studying mid to lower crust, the upper mantle, or for things like tectonics. Now, as far as the active or man-made sources are concerned, we have there are essentially two main types that we'll think about today. The first is the, let me just move my screen a little bit out of the way. Okay, perfect. The first is the galvanic source shown here. And this sort of the archetypal example of a galvanic source is a grounded electric dipole. And one can envision different types of receivers. For example, here we've got a voltmeter, which measures electric fields, and an induction coil, which measures dB/dt. And there's other types of receivers that can be envisioned. And this is the key, sort of the main characteristic of the grounded dipole or galvanic source is that the source makes direct electrical connection to the ground through the injection of a current, similar to electrical resistivity tomography. The key difference, of course, between this galvanic method of CSEM and ERT is that you have a time varying current that you're introducing into the ground. And the sources here, as you see here, can get quite elaborate and sophisticated. So the other main type of active source is the inductive source. There's a couple of different types. There's an inductive loop source, which we'll show here, generally laid out as a square of some side length, L. And you can put an induction coil in the middle, in the center of the loop, or you can put it outside the loop. And in this picture here from Malta, we're showing a time domain exploration survey for groundwater. Here we have a 10 by 10 loop, a transmitter loop with a centrally located induction coil receiver. And we can energize the transmitter loop with a certain transient disturbance. It's under our control pretty well how we want to do it. But in many cases, it could be, for example, a ramp off and a fairly abrupt ramp off from a steady value to 0 over a short period of time. And the key thing here, the main difference between the galvanic sources and the inductive sources are that the inductive sources are flux linked through the magnetic field. There's no electrical connection to the ground. Another type of inductive source is these portable loop systems, and these operate primarily in the frequency domain. You can see a couple here. This is the EM31. This is the EM34. They're called, made by Geonics, and other companies make them, and they're called terrain conductivity meters. And they feature usually a small loop of radius A, and oftentimes a similar or identical loop acting as the receiver, as an induction coil receiver. And one can go around at fixed offset or at some variable offset, making measurements of apparent conductivity and things like that. In this case, in the frequency domain, the transmission is a sinusoid or a number of sinusoids, and they typically have frequencies of 10 kilohertz in that range, and they're probing in the up to several tens of meters. So what about magnetotellurics versus control source method? Well, here's a way of looking at it. You can think about magnetotellurics, if you want, as a type of control source EM method, but with a very large loop, carrying, for example, quite a complicated fluctuating current in the time domain. And here the loop is laid out near the coastline, and we have a strike direction of that in the coastline direction. And so if you could imagine that there's little ants working under the wire, like for example, at position 1, this ant sees a primary driving field in the strike direction. So that ant could be making TE measurements, for example. And this little ant under here is seeing a driving electric field going in the perpendicular to strike direction, making TM measurements. And we'll see towards the end of the talk, when we talk about analog scale modeling, that this isn't such a far-fetched scenario and can be reproduced in the laboratory. Okay, so when we're talking about, this is very important topic. When we're talking about EM induction, we're making a quasistatic approximation. A quasistatic regime is one in which the physical length scale of your survey area is small compared to the EM wavelength at the operating frequency. For example, if you're interested in frequencies of about 1 hertz, let's say, then your wavelength is about 3/4 of the Earth-Moon distance, which is very large. If you're interested in frequencies of about 1 kilohertz, that wavelength is still large, 300 kilometers. And at 1 megahertz, it's 300 meters. Now we know that the EM wave velocity in water is very fast. It's roughly 1/9 of the speed of light in vacuum, so that an EM wave can propagate across a 10-kilometer wide survey area in only 300 microseconds. And it's even faster in the ground. So the approximation we're going to use is that the velocity of the EM wave is in fact infinite. So we say that C goes to infinity. This has some very interesting and profound implications that we're going to discuss. One of them is that the electromagnetic wave at every location within the survey area has essentially the same phase, because the wavelength is so large, which is the phase of the transmitter. And in fact, the entire Earth in the limit as C goes to infinity is in phase with the source. So some folks have said that the entire Earth breathes along with the source. So what does that, what other things does that imply when we say or presume that the EM wave velocity is infinite? Well, here's the well-known formula for the EM wave velocity. You notice that if you make C go to infinity, then effectively the permittivity goes to 0 or vanishes in the quasistatic formulation. So here are some of the implications of having 0 permittivity. Number 1, we know that electrical permittivity governs all manner of charge polarization phenomena. These are ones that are that describe the response of bound charges to, say, an applied electric field. So that all bound charge responses are negligible in the EM method. We know also that permittivity, epsilon naught, sets the scale for the Coulomb force between charges. Thus, on the MQS approximation, we neglect Coulomb's law, or the electrostatic interaction between charges, when we're working in this regime. And finally, we know that displacement current also scales with permeability, linearly in fact, and thus displacement current and concomitantly the EM wave is neglected. So all of these effects, 1, 2, 3, can be summarized by saying that we ignore capacitive effects. Now they're present in reality, there's no mistake about it. They occur and they're useful and geophysical methods are based on them. They're just simply not in the MQS approximation. When you make such an approximation to the governing laws of physics, you have to give something up. And this is what we give up. And for some scientists who are familiar with electromagnetic waves, for example, the idea of giving up Coulomb's law is difficult to countenance with their intuition. And so we have sometimes we have a interesting job as EM induction people to explain to them that yes, we do neglect Coulomb's law and it's perfectly fine, as I will show. So what we have without waves is a diffusion process. And this is true, EM induction is a diffusion process regardless of the regularity of the transient disturbance that generates it, even if it's periodic. Okay, and we can look at this by analogy with heat conduction in the soil, a very simple and intuitive physical scenario. So for example, this formula here describes, and you'll recognize it right away as the same formula for the EM induction in a skin depth from a planar signal incident on a uniform Earth. Now this is the same expression with the same physics for the temperature profile in a soil column with depth. So imagine, if you will, that we have an oscillating seasonal oscillation in the soil temperature, which is T0 at the surface. This means that the temperature is maximum in summertime, as you'd expect, and it's minimum in the winter. Now, at a certain number of skin depths, because of the thermal conductivity of the soil, and we can see there's a phase term here, that actually at pi/2 skin depths, the signal is 90 degrees out of phase with the signal at the surface, and it's reduced in amplitude. And so in fact, as you see here and here, is that the soil temperature at that depth is actually greatest in the autumn and reaches a minimum in the spring. And we can see that this difference in the seasonal variation damps out as we go down 2, 3, 4 skin depths. And it obeys just the same equations as we do in the EM. So we have a phase that varies linearly with depth, as you can see here with Z. And we also have a periodic driving function. But interestingly, no wave physics is involved. So you can call it periodic driven diffusion. Another aspect of EM induction, which is rather interesting and has some important ramifications, is that the response that we measure is in the MQS approximation, or the inductive regime, is instantaneous everywhere. So through the entire Earth. And we can easily see this by examining a simple problem, the stepoff response of a line source in a uniform hole space. So we know that the solution to the full damped wave equation, which includes the displacement current, is given by this big formula here. Look carefully and you'll see the appearance of the Heaviside function in the equation, which indicates that the solution, that the response does not begin at time equals 0, but actually begins after the speed of light propagation time. In other words, it takes a finite time for the signal to reach the receiver. That's when you include the full displacement current. Now, the same solution to the same problem, the same physical problem, but without displacement current, it reduces to a diffusion equation and has this familiar solution here. And notice that the diffusive response at all offsets is easily shown to begin immediately everywhere, no matter what the receiver offset is, at time 0. Okay, And the net effect of this, and we'll show in the next slide, is that displacement current can be safely neglected if all of your measurements are made at times that are greatly exceed the speed of light propagation time. So this graph here from Orstaglio and Hohmann, 1989, shows it quite well. What we're showing here is the electric field, the step-off response as a function of time. Notice that we're measuring here in nanoseconds, very early times. The symbols show the full damped wave equation, and the arrows here show what we might call the first break. So we know with electromagnetic wave propagation, for example, those who do GPR understand this, that we don't see a signal in our data until enough time has elapsed that the signal has gone down to the target and reflected back at whatever the speed of light in the material is. This arrow indicates that time, and you notice before the arrow there's no signal, and then there's the arrow, which is the first break, and then you get the decay term following that, where the diffusive behavior takes over. Contrary to that, whatever is the source receiver offset, we see that the diffusive response smoothly goes to 0 and X actually is non-zero even at time 0, and then grows, and then there's sort of an exponential decay tail there. And so the MQS approximation is an excellent one as long as you make your measurements in the times after the step off where these two curves coincide. So if, for example, at 300 meters, it's everywhere beyond 100 nanoseconds, even very close in this material at 0.01 Siemens per meter, 0.01 Siemens per meter. As long as you're making measurements more than a handful of nanoseconds, like 10 or 50 nanoseconds, which is routine in EM surveying, you can neglect displacement current and neglect the effect of the EM wave. Okay, so now here's another thing, is that in the ground, there are charge carriers, we all know that. Now, some of these are free or quasi-free to migrate or drift from place to place within the geological medium, whereas other charges are bound to lattice atoms or material interfaces, or in this case, within the molecular structure. So this is water. Now, when you're thinking about electromagnetic waves, the bound charges play a big role. For example, in GPR, it's the rotation of the water molecule or the polarization of the water molecule that slows the wave velocity and enables us to find interfaces and differences in water content, water table, so forth. But it's the bound charges that are responsible for the reflections. Now, we recognize that the polarization phenomena are caused by the charge distribution or a polarizability of the material, which is governed or described by epsilon. So when we set epsilon equals 0, we're neglecting all of this stuff that involves things like rotation of water molecules, things that are associated with permittivity. On the other hand, in CSEM, what we are energizing and what we are measuring is the migration of charge from place to place within the material. So for example, in a semiconductor, you've got holes and positive charges and ions hopping about from site to site. And saturated medium, which is more commonly looked at, especially in the near surface, we have pore fluid electrolytes, we have solid grains, and it's the ions, the dissolved ions, that carry the charge migrate from place to place within the electrolyte that we call the induced, that is responsible for the induced current. And you can see that here, that the positive charges go one way and the negative charges go a different way. They're confined to the pore space, so they take these kind of tortuous paths. Now, the important thing to recognize is that in EM induction is that all of the ionic charge carriers are presumed to have the same mobility in the material. So if they have different mobilities, you'll get a charge separation. You know, if the negatives are dragging somehow compared to the positives, then you're going to generate things like self-potentials and streaming potentials, etc., which are important, and they exist, and they are oftentimes they're the basis for entire geophysical methods, but they're not part of EM induction, and they're not included in the approximations we use. So the way you can summarize all of this up, if you want, is to sort of say or think that the world of EM induction is really a world in which all charges are mobile. Now we need to talk about boundary conditions, because this is an interesting aspect of what we do. And traditionally, in electromagnetic wave phenomena, we have reflection, we have refraction at material boundaries. In optics, seismics, all these things, generally we have a derivation of Snell's law from things like Fermat's least time principle, which is that the path from position A to B is the fastest time that it takes for the signal to get from A to B. However, in the NQS or induction regime, all the signals travel instantaneously in every medium. So we can't use this wave-based explanation for the behavior of the EM field at the boundary condition. In fact, EM induction cannot be explained by wave physics. So how do we explain boundary conditions in induction regime? Well, one way to look at it is simply a case of the conservation of mass and energy. And here's an example. Here we have a line of cadets marching, and they're in the grass, okay, lines of cadets. So they're marching in the grass fairly quickly, okay? And they approach a different medium, which is slower, mud. So they get sort of slowed down in the mud. Notice that this guy sees the mud first. So he slows down earlier than this fellow who's still walking through the fast grass, sees it later, and then eventually will slow down. But at the bottom line of it is that they will refract into the medium, and that you will find an accumulation of cadets in the mud and a relative depletion of these cadets in the grass. You see there's less density, more density. And so in the EM case, at conductivity boundaries, and we're dealing with the ionic charge carriers, there's going to be a change in the mobility of ionic charge carriers as one goes from a relatively fast to a relatively slow medium. And that when the charge carriers cross the interface, there's going to be accumulation of charges on one side and a depletion on the other. So we get what appears to be a buildup on the boundary. And notice though that there is no sudden appearance of new cadets at the interface. They don't spring out of nowhere, and there's no disappearance of cadets into the vacuum at the interface. So there's a conservation of a mass and energy. Okay, changing gears a little bit, I want to talk a little bit about induction and inductors, because after all, this is a talk about induction. So let's think about this from a very simple terms of RLC circuits. So as you probably know, there's three primary types of passive elements: as resistors, inductors, and capacitors. So what do each of these do? Well, we know, here's some resistors. We know that resistors are designed to reduce the electric current flow in a circuit. We also know that inductors are designed to prevent rapid changes of electric current flow in a circuit. And we also know that capacitors are designed to filter out or remove slow changes of electric current flow in a circuit. And the earth, as it happens, can behave as a resistor, with the ERT method, and the inductor, EM induction, capacitor, we need to start thinking about GPR. What are some of the hydraulic, okay, so to understand the operational principle of an inductor, or what inductance means, it's useful to think about a hydraulic analogy, because we know that electric current flow in a circuit is in many ways quite similar to water flow in a system of pipes. Okay, so let's go through. Resistor is, in the hydraulic case, is equivalent to a constriction in a pipe. So that requires more water pressure to pass the same amount of water as it would through an unconstricted pipe. Now, what about an inductor? In the hydraulic analogy, an inductor is essentially equivalent to a paddle wheel in a flow with very heavy blades. And it has some inertia. That's the key point. The heavy blades carry inertia. What that does is it damps out rapid changes in the flow. So if I suddenly increase the water flow through this system, there'll be some resistance of the paddle wheel because it has some mass and inertia that will at first resist that flow. But eventually, if you provide enough time, the paddle wheel will get up to speed and you will have a normal electric current flow in the steady state. So that's the hydraulic analogy of what an inductor is. And for a capacitor, just for completeness sakes, a capacitor is equivalent in the hydraulic analogy to a rubber sheet which is sealed inside a pipe. So that if you put additional water pressure here coming from the right, it's going to stretch the sheet, but it's not going to allow the water to pass through it. And so you can think of a capacitor as a device which stores water when you have a sudden increase in driving force, but it doesn't allow water to pass. Similarly, in the electrical case, you can regard a capacitor similarly as a device that stores electric charge but doesn't allow current to pass through. So focusing now on the induction part, this is a very famous diagram from Grant and West, and Gordon West was on my committee at A&M, not A&M, that's where I am now, at University of Toronto. And yeah, so he's a wonderful, wonderful person. If you've had the chance to meet him, you will know what I mean. Anyway, so this is essentially the basic physics, and I won't go through it because we all know that there's a time-dependent magnetic field fluxes through a conductor. Response of the conductor is to induce some eddy currents or vortex currents, which produce a secondary field measured at the receiver. And it's the principle by which, for example, an airport metal detector works. And you can see that if you have your keys in your pocket, you're going to get an anomalous signal at the receiver, and the thing will go beep, beep, beep. So we know that the purpose of a metal detector is to make sure passengers place their keys on the tray before they go through the metal detector, and they don't forget and leave them in their pockets. So let's look at self-inductance in more detail. So self-inductance measures the tendency of a conductive body to, as I say, to oppose a sudden change in electric current flowing through it, just as the paddle wheel, with its inertia, tends to resist a sudden change in fluid flow. Inertia, then, is the resistance of any physical object to a change in velocity, its velocity. And we're very familiar with Newton's law. Here you can see that the mass carries inertia, so that you require, for a larger mass, you require a larger force to achieve the same change in velocity. So the mass is the equivalent here to an inductor. In Faraday's law, you can see that a device or part of the earth has a certain inductance, which means that you require a bigger, if it has a large inductance, you require a bigger voltage to get the same change in electric current. And mutual inductance describes the magnetic coupling between two conductors. So here we have a current in one coil producing a time-varying magnetic field, which induces a current in another coil according to its geometric properties and induces an EMF or voltage in the loop. And mutual inductance of these two guys is a measure of the magnetic flux through the second coil due to the electric current flowing in the first one. So how does this apply to geophysics? Here, for example, is a transmitter loop, inductively coupled loop, lying on the ground. You energize it with a disturbance, some kind of transient disturbance. You produce a time-varying magnetic field. The Earth is a good conductor, so it will respond by setting up a vortex current, as we discussed. And that in turn, at time one, that in turn will produce another time-varying field, which sets up further down another electric current system, a vortex eddy current system. And so it goes as the system goes T1, T2, all the way down until it finally dissipates through loss of energy. And what we can measure here in the receiver is the sum total as a function of time of the magnetic fields by all of these mutually coupled, conceptually mutually coupled loops. And we know that the shape of the time variation at the receiver coil is diagnostic of these material properties, sigma 1 and H and sigma 2, because the ability of the material to establish a current is going to depend on the electrical conductivity. Okay, so this is a very simple experiment we did in order to look at the effect of inductance on an EM response. So we had a loop source here. In this case, it's reasonably small. It's an EM63. It's a time domain EM device. It's used as a metal detector, but it's effectively time domain EM. We have a receiver coil here. So we made some measurements over soil, just plain old soil. We got a fairly small response, a shut-off response, as a function of time after switch off of the signal, shown by the solid and dashed line. We have a change in sign, of course, a dashed line. And then we placed in the ground a intact copper ring, just a simple ring of copper, and placed it in the ground. We went over it again, and we got what we thought we'd get, which was a pure exponential decay, and until it went back to the background. It died out and went to background. And so what that exponential decay is an azimuthally circulating eddy current within the ring. And so you can see, even though it's a very filamentary ring, nothing really big about it, it's not a thick ring, it's a thin ring, we get a substantially large response, a couple of orders of magnitude higher. Then what we did, we took a pair of pliers like this, and we cut the ring. And so we disrupted the circuit, we put it back on the ground, and what we found is that the signal went virtually to zero. The additional signal from the object went to zero. And the reason for that is that we created what effectively is an open circuit and doesn't have eddy current cannot flow here. And so what we did was we dramatically changed the inductance of the target. We did not change the electrical conductivity with a narrow cut. It has the same amount of metal, put in the same place, but all we did was change the geometric arrangement of that good conductor, and we got a very, very different response. And this plays a role in understanding EM induction responses in terms of their sensitivity to inductance. So for example, here is a survey area, hypothetical, this in plan view, and it's supposed to be like an area of fractured rocks. So these are fractures here, conductive fractures. And what I've done is I've shaded in all of the areas that are enclosed by a continuous perimeter of these conductive fractures. So in other words, these are areas where currents can flow in a closed loop. And these are the areas that enclose them, and or that are enclosed by them, excuse me. And so if you were to expose this survey area to an external time varying flux, you would expect that these areas of exposure of flux by Faraday's law would generate currents flowing through these perimeters, and that would govern the EM response. Now, contrast that with something that may be called percolation theory or something like that, where you do have a through-going current pathway through your survey area. But we know that a filamentary piece of wire has no inductance, so cannot be responsible. This cannot be responsible for the EM, for any EM response we have. you know, it's going to have to close somewhere outside the survey area. So there could be a role to play. But the important point is that if you were a subscriber to pure percolation theory, you would probably argue that if you took away this critical element and disrupted the through-going path, you would kill the EM response. But it's not likely to be the case, because you would still have probably what's a much more significant contributor of these areas of closed flow. And so that a critical element doesn't really change the response, probably doesn't change the response of much at all to your excitation. So percolation theory may play a role, but it's probably not as important as in my view, as this contribution, where the EM response is going to be really governed by the total area enclosed by a conductive perimeter. And don't forget, there's interesting features going on. These are going to be mutually inducting as well. There's going to be some mutual inductance, so there could be some cancellation and reinforcement. And it's going to depend on the areas of the objects and their separation and things like that. Okay, so changing gears a little bit more. Here's somebody who's mapped a fault, and you can see that this fault is really complex. And in fact, Earth has complexity at all different levels of scale. So you look at a soil, you see heterogeneity. You zoom out, you look at an outcrop, you see a different type of heterogeneity. Even the regional structure has different heterogeneity. In fact, Earth has nested heterogeneity at all length scales, from microscopic all the way up to global, a continuum, not just these three that I've shown here. So how can we understand EM induction in the presence of such length scale dependent heterogeneity? Here's an example of a fracture network that's mapped out in a rock by these guys. Typical, nothing unusual about it. If we could imagine exciting it with some external changing flux, dB/dt, we're going to get a migration of charge carriers, or essentially a random walk. And notice that because of the geometric hierarchy of the fractures, is that this random walk will not take even steps, but will take some longer steps and some smaller steps. And so we would not be surprised to find out that those differences in path lengths are going to make a significant impact on our measurements. So here's an example. In classical diffusion, if you start a random walker at time equals 0, we know if it's classically diffusing that at some time t, then the average square displacement of that particle from its starting point will scale linearly with time. However, if some of the path lengths are large and some are small, there's heavy tails to the distribution of path lengths, then at some time t, the random walker does not obey a classical trajectory, but rather in the case, for example, here of super diffusion, it can exhibit a much larger x squared displacement at the same time. And so in fact, you can show that the time does not scale linearly, but scales to some power beta, which can be small, in which case you might have subdiffusion. It would stay around the origin if all the paths were preferentially small, or it could be big, like in this case. So everyone knows James Clerk Maxwell. He was a classical physicist who gave us all the equations we use and put them all together in EM, along with his colleagues, Faraday, Ampere, etc. But I don't believe that he considered materials like the one I showed you with the soil that exhibit length scale dependent heterogeneity. I mean, he may have, but I'm not aware that he did. And so keep that in mind as we go forward. This is the equation for the diffusion of electric fields into the earth, or into a medium of conductivity sigma. And we all know that EM is really responding, or EM data is somehow a spatial average of the subsurface electrical conductivity over the region we're looking, like within the footprint of the instrument. And mathematicians will tell you that solutions to these types of equations are always smoother, in fact, 1 degree smoother than their coefficients. Okay, so and that accords with our intuition. Now, when we make measurements in the field, almost invariably, we find that the CSEM response, in this case, it's the apparent conductivity, is quite rough, right? It has fluctuations on many different length scales. And so we would expect this is the CSEM response from the instrument. We'd expect the underlying electrical conductivity to be even rougher, in fact, 1 degree rougher than the response. So in order to account for that roughness, one can adjust the time derivative in Maxwell's equations. And this has been done in not only in geophysics or all over in many different areas of physics. For example, Michel Caputo many years ago proposed a similar idea in elasticity, and you replace the integer order time derivative or space derivative if you want with a fractional term with beta, and this is the same beta that governs the square displacement term. And so this equation here, if you solve it, produces a distribution of currents that has those heavy tails that we talked about. So again, we suspect that almost wherever we go, the geological media is going to exhibit this type of length scale heterogeneity. I mean, I can't think of a place where it doesn't. And what it means is that the signals that we see have, as a function of distance, and here I am making some measurements, they have long range persistent correlation. So you'll see some longer wavelength feature superimposed on some moderate ones and then some fine scales. It's cycles upon cycles upon cycles. And people who study the Dow Jones index know very well what I'm talking about. But if you take if you look at the increments of these, in other words, the difference between one reading to the next, they come out to be white noise. And this is a typical behavior for this type of structure. If you take a power spectrum of this response as a power spectrum, you get a power law with some slope, and the slope, it turns out, is the same beta value that we've been talking about. So let's look at what does the beta value imply. So we can look at the response, EM response, apparent conductivity, as a function of different lithologies. So here in Texas, we have some granite, we have some sandstone, we have some maroon soil. And so we make our measurement of apparent conductivity with our device, the frequent loop-loop device. And we see over the granite, we get some larger scale. We get smaller ones as well, but we get some significantly more long wavelength fluctuations, sandstone somewhere in between. And then as you'd expect, over the soil, we get mostly fine scale fluctuations. So we can take power spectrum of all of those parts of the signal. In the granite, we get quite a steep power law. These are close to 0 for the increments. We get a steep power law, and then in the maroon soil, we get a relatively shallow one. And what this means is that a relatively shallow slope means that substantially or preferentially more power is contained in the signal at these higher wave numbers or shorter wavelengths. So the beta value shown here is indicating the relative contribution of large scale fluctuations to small scale fluctuations. So not surprisingly, with the granite, which is intact, has a few fractures and weathered, but largely intact, we get much stronger contribution, more power in the signal because it's a steeper slope, so it goes up faster. In the short wave number regime, or in other words, the long wavelength structure, which we saw in the previous diagram. So we've been talking about geological materials having this type of heterogeneity, but what about man-made materials? We know that man-made materials like a pipe are going to be geometrically more regular. They're not going to have, we don't expect them to have nested heterogeneity by any stretch. So we did this experiment. We moved our loops over the soil, and here's our response. And we get a power law signal as we'd expect, because the soil does have this nested heterogeneity. But when you put the pipe in, you get this large signal here, a dipolar signal due to the pipe. And if you plot the power spectrum of a series like this, you get a characteristic peak. It's not it's no longer linear, but it's rather has a peak at the natural, at the spectrum, at a value that is indicative of the size of the pipe. And so what we can say is that the anthropogenic targets don't show this same effect because they don't have this nested heterogeneity because they're more geometrically regular. And this is important, has many applications that are well known. For example, in radar at sea, to detect ships, you have to detect ships in heavy seas where there's using radar. You get what they call sea clutter, which is like this, and then you see the target. So it's a way of finding targets in the at sea by looking for departures from the power law spectrum, and we see that here in geophysics as well. Okay, I got 3 more points, 3 more different topics, and then a final thought to give you. I want to talk briefly about Poynting's theorem because there's some interesting things here that could potentially be somewhat counterintuitive at first. Okay, so here's Poynting's theorem, and it's very simple. It tells you that the loss of electromagnetic energy in some volume can be partitioned into 2 parts. First, the energy loss due to Joule heating, ohmic dissipation, heating the material. And second, the part that escapes, the power flux through the bounding surface. Now, in the induction approximation, in the inductive regime, epsilon 0, so we don't have any electrical energy, which accords with our idea that charges don't play a significant role, but currents play a role. We have magnetic energy, and it's equal to the loss of magnetic energy at any given point is equal to the amount of heat produced at that point or dissipated, lost to heat, plus the divergence of energy away. So it's the stuff that goes away. Okay, now to understand the Poynting vector and the fact that the contours of the Poynting vector describe energy flow is helpful again to look at a circuit. So we have a simple resistive circuit. We have a battery here with some kind of voltage, and then which is a source or a seat of EMF or energy, and we have 2 resistors. Now, naively, you would think that energy flows in the wire because that's where the currents flow, that's where all the action's going on. There's nothing going on anywhere else, and energy flow. If you were to plot the energy flow, you would simply plot the wire, but it's not the case. Is that energy flows actually from the battery to the sinks of energy through the free space. Okay, so in the middle of this, in the circuit. And it's not that surprising when you think about it, because if you think about a current carrying wire, current flowing in the wire, the magnetic field is curling around, E cross B is radially outward into free space. So it kind of makes a little bit of sense, but it's a little bit counterintuitive to begin with. However, we can use this kind of idea to understand what happens when we try to explore for something like a resistive layer, like an oil-bearing layer. So I'm going to talk about an electric dipole on the surface of the Earth, air above, below. We can think about the inline profile, or we can think about a broadside profile. Today we'll focus on the inline profile. So what I plotted here is that frequency of a hertz. So this is frequency domain. I plotted the EX and EZ components from the transmitter. Here's my layer. But what I want to focus on is the energy flow. So what I've done is I plotted here in this diagram, and this is work, by the way, that Alan Shave has helped me with, and as he has much of this presentation, I want to point out, is that we have arrows that go up or down, the direction. Okay, what we're plotting here is the direction of the Poynting vector and color coding it. So that green arrows point down, red arrows or purple arrows point up. So what we see is that when we turn on the transmitter, we get energy flowing up, over, and then down, back down on the Earth, vertically downward. See, 180 is down. So it's almost like a planar signal coming down on the Earth. And then when it sees a resistor, like in the circuit case, where the energy wants to flow through the resistive part of the system, energy here preferentially flows through this resistive channel back to the transmitter. And so for that reason, we can, because of the energy flow concentration here, we call it a waveguide effect, a kind of misnomer, but never mind, is that we see that there's a capability for this system to detect resistive layers at depth. Contrast that with a conductive layer. Here are the field patterns, but we're interested here in the streamlines of energy. Energy comes up and over as before, down as a planar signal. Everything's great, yay. You go down, it doesn't see the conductor, doesn't want to flow necessarily through the conductor, wants to flow through the resistive parts. So we get a surfeit, or a deficit, I should say, of energy flowing in the oil-bearing or resistive layer. Consequently, it's in the conductor. So consequently, a conductive layer is more difficult to see with this setup. Okay, 2 more topics, and then a final thought. Separability. Now, when you were a undergraduate, I hope, or you may have, and if you haven't, that's fine. You used separation of variables to solve Laplace's equation, to solve Helmholtz equation. It's a very widely used analytic technique. In fact, we've already used it to determine the soil profile, temperature profile. But you know, when I studied it, I thought, okay, this is valid for idealized systems only for very ideal systems. I wasn't sure if it was actually found in realistic complex settings. And I knew that the solutions that one obtained using separation of variables were unique solutions. So I know that for some systems you had a separable response, by which I mean that the solution is a product of a function of space onto a function of time. So we tested that idea with a very simple model. We buried an aluminum plate and then measured the response of it. And this is 2 plates, so I'm just going to show you 1 plate example. So we have a single horizontal plate that's set in the ground. We went over it with the EM63 again. And what we found is that, amazingly, is that each station obeyed the same time response. So as we went across the plate, every station, every single station here had the shape of the transient was exactly the same. Okay, that's interesting. But furthermore, so too at a given time gate, so at the first, if we just only look at the first time gate, we get a dipolar response. Look at the second time gate, and we have to scale it because it's going to be a bit lower, but it has the same shape. So all of the time gate responses going across the plate had the same shape. Now there's not perfect because there's some noise here due to the early times, and so it could be something going on, maybe with the cart moving around. But the main thing is that, yeah, wow, okay, even in the field example, we get a separate, we can decompose the response into a function purely of space and a function purely of time. And we did the same thing with the vertical plate. Every station had this shape of decay, and every time gate had this shape of spatial response, so we could decompose it. So separability holds even in the field. And I'm like, okay, wow, that was interesting. Maybe it's just me, but I found it interesting. Okay, we're going to go back to our ants. This is the last topic, and this is called similitude, and then a final thought. So with similitude, what it means, and this is well described in classic textbooks like Stratton of 1942, is that this product here is invariant in electromagnetic induction. In other words, you get the same EM response for a model that has this product being the same. So in other words, I can change if I was doing modeling, for example, I can change D and change conductivity and frequency at the same time. If I keep the product the same, I'll get exactly the same response. Okay, so excuse me. And this was used by people like Dassault in 1966, who developed it. Here's the wire. There's an ant under here. This is supposed to be the MT again. Okay, so he was modeling an MT system, and he did it in the lab. But then he knew by the principle of similitude that if he organized his conductivities, frequencies, and length scales according to what he wanted to model in the geophysical, in the outside world, he could then reproduce what he would find in the outside world with a lab scale. Now, we don't do this anymore. This analog scale modeling is not often done. Sometimes some people do it, but it's not often done. But we do have numerical simulations. And the principle of similitude is extremely important as a debugging tool. If you have a code that is that you would like to think produces faithful EM responses, then your code should scale up and down according to this principle. You should be able to change your model, change your length scale, change your frequencies, and get exactly the same response to machine precision. And I know this has helped me, for example, finding some rather interesting bugs in my code that they don't scale properly. So if you have code, scale it up and down and use that principle, and that will, you may, if you're having trouble, you might find a bug. Okay, it's my final thought. This is just for fun. Okay, what I want to end with is just to remind people, or at least not so much remind people, but maybe tell people my what I'm thinking is that research can go extremely slowly. Okay, for example, here's just one example just for fun. It took mankind several millennia to realize, to fully realize and to properly appreciate that wheels could be attached to luggage to make life simpler. So here's an early wheel from the archaeological era, 5,000 years ago, one of the first wheels ever found. And here's some luggage. This is a guy, a Roman guy from 2,000, 3,000 years ago, whatever, carrying his luggage, which presumably could get substantially heavy or at least uncomfortable if he carried it for a long time. So this is thousands of years ago. Now, it wasn't until 1961 that the first patent was announced for luggage wheels. Pullman or someone like that put wheels on luggage and made such an advance of labor-saving advance. So my question for you, this is slow progress of research, right? Thousands of years to get to here. My coffee table question for you, as you meet your colleagues via Zoom or hopefully in person and you can discuss things, is the question, why did Einstein carry his luggage? I mean, he was a smart guy, right? Presumably he carried his luggage around and presumably sometimes it was substantially heavy and uncomfortable. But a simple idea, 1 + 1, why didn't he put, why didn't Einstein use luggage wheels? Okay, so that's my question for you guys to contemplate as I finish and now finished my talk. Thank you very much for your attention, and I'll take questions if you have any at this point.
Oh, thank you very much, Mark. On behalf of everyone watching, I'd like to really thank you for that wonderful discussion and presentation on EM theory. And, clearly one thing I've found is that some of us do mathematics well and some of us do physics well, but there's very few people who do the mathematics and the physics together equally well. And you mentioned Nigel Edwards and Gordon West, and those two have always impressed me that they can see the physics happening and they can write down the mathematics, or they can look at a mathematical equation and they can see the physics in the equation. And I think you've shown that you're the next generation and you're carrying on that wonderful idea to be able to understand mathematics and physics together.
Does that mean I can't retire?
Well, no, it means you've got to find someone of the next generation to who carry on doing it.
Well,
so, as usual, it's open now to questions. And as usual, Syed is always first off the mark. Thank you, Syed, for your questions. Every single time he's got the first one in. Thanks for your information. So what I'll do, Mark, I'll read out the question so it gets in the record.
Okay, thank you.
Thanks for your informative talk. A basic question. Is the assumption of plane wave in magnetotellurics really valid in the quasi-stationary regime? Nonetheless, the thickness of the atmosphere is only 1,000 kilometers. I think it should be 100. Anyway, however, this distance is not enough for the plane wave assumption. As you mentioned, a 1 Hertz signal has 300,000 kilometer wavelength, and so we need at least 2 wavelengths to cross the near field limit. So we never reach the far field and plane wave in the air.
I would say that it's a safe enough assumption. That's a very good question. But if you think about the example of Dosso in the lab, or if you think about even the case of the ants working under the loop, I think if you find and you know, if you do the modeling, if you make the wire apparatus a little bit longer, you're going to get some end effects for sure, but I think those will die off as you get as you make the wires longer. And I would suspect there would be only a small effect due to due to the size. I think the size of the current sheet is big enough at most frequencies that you can use the plane wave approximation, but certainly could be modeled.
Yeah, of course. I recommend those of you who haven't read it to look back at the early papers of Kenyard and the discussions that Kenyard had with Waite, the correspondence that Kenyard and Waite had together on exactly this issue, and Waite's concern about the non-plane wave assumption, or the plane wave assumption rather. And then the following paper by Madden in 58 or 56 that discussed this. But I think in a number of people have looked at this, and it certainly is an issue in auroral zones and in along the equator, right? You have to worry about the non-plane wave effects.
Yeah, it's good. Yeah, very good.
Oh, okay. So Dennis Woods asks, where does a massive sulfide conductor fit into your analysis of geological versus anthropogenic conductors?
Well, that's a very good question, because of course in the metal we have a different kind of conduction mechanism, which I didn't really mention, which is the electrons. The basic idea, though, is that there's a certain mobility of the electrons inside a metal bearing a pure metal, for example, and so the material remains electrically neutral. So more or less from the induction point of view, everything still holds what I discussed. What is interesting, though, is when you have a metal electrolyte junction. So you have a change in conduction mechanism, which I didn't really discuss. You might think about induced polarization, or you might think about charges, charge carriers that are for some time trapped up against that junction, and in some sense producing a electrochemical kind of effect, which is really outside the realm of the EM induction. But for in the general scheme of things, if the electrons will have some mobility, and I think everything that we've said here holds. You think about the ions flowing in the pore fluid. You do have two signs. You do have positive and negative signs, whereas in the metal you just have the negatives. But because they flow in opposite directions, they contribute the same sense of current, electric current. So, and this is why I talked about having the same mobility. You don't want the one sign of charge carrier to drag with respect to the other.
Yeah, apropos sulfides, I think with regard to your experiment, you showed that cutting that ring made a huge difference. I've done some work up in Yellowknife, and I've done some work in the Thomson Nickel Belt, and I've done some work in Bathurst, and these are all pyrite sulfide mineralization. But up in Yellowknife, there's been no metamorphism, so the pyrite grains are not connected, which means that you've got very high resistivity. And in Bathurst, you've had a huge amount of metamorphism, and the pyrite grains are elongated in every direction, and it's very conducting sulfides. But in the Thomson Nickel Belt, or on the North American Central Plains anomaly, the pyrite grains are only connected in one direction along the fold hinges, and this creates a huge anisotropy. And I guess this is something you've not touched on. I really like your description of the distribution of conductivity, that we do have to be dealing with this in a more statistical way. But of course, it's a distribution in 3 different dimensions. So you're going to have these probability functions that might be different in the 3 different axes.
Yes, that's true, Alan, and that's a good point.
So Syed has another question. Electric permittivity is a function of frequency and it changes dramatically, especially in water, while it does not change as much in solids. So is it possible that the variations you showed in the power spectrums were due to the water content and could not have such strong correlation in solids and lithology?
Oops. Well, you know, certainly with at the low frequencies we're involved at, and if the device is truly working in the inductive regime, then all these polarization phenomena can be neglected. And I would think that this rotation of water molecules, et cetera, isn't really going to affect the inductive response, because it really is not going to kick in until you get into the upper megahertz, because that would be a displacement current effect. So we saw with that, as long as you're making measurements a nanosecond on longer than several nanoseconds after your disturbance in your source, then you can neglect these polarization effects. There is, so if you're at nanoseconds, that's like megahertz or even gigahertz, right? So if you're in the megahertz to gigahertz range in the frequency, looking at it in frequencies, then yes, I think you ought to look at the full damped wave solution.
Okay, is there any more questions for Mark? If not, I'd like to thank Mark again for absolutely wonderful EMinar. And it's a brilliant, you kicked us off brilliantly, Mark, and just like to bring us back to where we were, if I find it. Oh, Chet just jumped in. Could you please elaborate on the introduction of fractional derivatives into the governing equations of EM induction? Where does the physics of anomalously diffusing charges arise in a mathematical description? Thank you, Chet. Yeah, well, I better go and clean my teeth again. This is going to be a lot.
Well, hi, Chet. I'll just be brief. It comes into play, as you know, in the exchange of the integer order with the derivative order, and the solutions for the when you have a fractional order derivative have distributions with these heavy tails sort of thing, and it's what we see in the power spectrum, because you can equate the slope of the power spectrum to these heavy tail distributions, and again these heavy tail distributions are solutions to the fractional Maxwell's equations. So when you have charges physically, when you have charges that follow pathways that don't have Gaussian distributed steps, but have some long ones and some short ones, then you get these heavy tailed distributions.
Okay, again, then I'll just thank very much Mark for setting us off on this wonderful journey of EMinar Season 2. And before we close, I'll just remind everybody that the next week we have Jeffrey Love on mapping a magnetic substorm. So thanks again, Mark, and see everybody next week.
Bye. Thank you. Bye-bye.